Okay, everybody, welcome to our note session for today. What I want you to do is get out your packets from this unit, and you're going to flip in your packet. All right, we've gone through all this. As long as everything's in order, right, we're going to go past the gravity sim, Newton's laws of motion, our notes, Newton's second law, or F equals ma practice problems, Newton's second law, Newton's third law, which we just did. We're going to get to this guided free body diagram notes. So let's start here. And it doesn't want to focus. There we go. So today what we want to do just quickly is go over and be able to explain 5 forces that work on an object. So when we draw a free body diagram, we're drawing all the forces that are at work on that particular object, not interactions between 2 different objects, but just forces acting on one object. We want to be able to explain how the motion of an object is affected when balanced and unbalanced forces act on it. And we're going to be drawing, right? We're going to be drawing this week free body diagrams. So we want to be able to draw a free body diagram and then interpret one if we see it. So if we look at scenario 1, right? If we have a book at rest on a table, it says diagram, the force is acting on the book. So the book's at rest. You can see here that it's in bold. And what we want to do is diagram all the forces. So you then have to think to yourself, okay, what are the types of forces that are working on the object? And when we say working, you can think of this as acting on the object, right? Remember, this is not interactions between 2 objects. This is just what forces are acting on an object at one time. Well, if something's at rest, we're going to have the normal force, right, which is our support force. And we're going to have gravity, which is the object's weight. So you can see here, and you can draw this in on your notes, okay, that we've got a book that's sitting atop a table. So this is the scenario. And so we can represent the free body diagram. We can represent the object as a dot. So the dot can be the object, right? Or sometimes we'll see a square, and this comes from our concept builders, right? Our concept builders can be a square. If we're not doing a concept builder and we're asked to draw a free body diagram, sometimes it's easier, once again, just to draw the dot. So you draw a dot, and then you draw the vectors. So the vector down starts from our object and has an arrow down here. So I'm just going to make that a little bit bigger. And then this is F of G. This is the force of gravity, or the weight of the object pulling down. And this upward force is the normal force, Fn. It's the supportive force that's pushing up on the book. Now, because these 2 forces are equal, I'm going to draw these 2 little lines. And those lines are called congruency lines. And you learn about those in math. And what that means is that vector, or the vector F of n, is equal to, right, the vector F of G. So once again, those congruency lines mean that the normal force is equal to gravity, right? That's what those congruency lines mean right here. And so if we wanted to explain this, IE stands for in example. If we saw this, right, this free body diagram, this would be our explanation, right? Gravity pulls down on the object, creating weight. The normal force, a supportive force, pushes from the surface of the book, pushes from the surface the book sits on, right? And so when we look at this and we have equal forces, we can either have no motion, which is at rest, or we can have constant velocity. And in this case, we've got no motion because it's telling us it's a book at rest, right? So we should know that. And therefore, the book has no acceleration. So let's take a look at the girl. A girl is suspended motionless. So if a girl is suspended motionless, right? A girl is suspended motionless from the ceiling by a rope. Diagram the forces acting on the girl as she holds onto the rope. Well, tension, hopefully remember tension is Ft, and gravity, which causes weight, is Fg. So here we have the girl, it says she's motionless. I want to bring that to our attention. And we know that she's hanging by a rope. So that's why it's tension, right? Because this is a more specific applied force. So instead of saying applied force, remember we use tension. So if the tension, right, is coming from this upward direction, we've got Ft up, and then down, we have F of G, which is her weight. Now these two things are equal, and they're equal because she is motionless, or in this case, at rest, right? So gravity pulls down on the girl, creating weight. Tension is upward through the rope, right? And if you want to think of this as your applied force, just in parentheses, you can put applied, right? That's your applied force. We say tension because, once again, tension is more specific than the applied force. It is a type of applied force. Now, is she accelerating? That's what we have to ask ourselves. And once again, if we have equal forces, they can be at rest or they can be at constant velocity. Therefore, there is no acceleration because she's at rest. Now, is there motion? Well, she's not moving, so there's no motion. So we always want to talk about each, right? If we're asked to explain, right, the forces, we want to talk about each force and what it's doing. We want to talk about if the object then is accelerating, and if there is motion, what type of motion? Where are they moving? What direction are they moving? And is it positive or negative as far as acceleration or deceleration? And then, once again, the direction there for motion. Okay, so I'm going to put this for motion, direction. And the acceleration, we can say, is either positive or negative at times. Now, in both of these examples, we did not have acceleration, right? There's no acceleration and there was no motion. So let's take a look and see this next one. Maybe we have some motion or acceleration. So a skydiver falling through the atmosphere, right, which is our sky, says do not neglect or disregard. So do not disregard air resistance. So here's our skydiver. They're just falling through the sky. So F of AIR, please remember that's air resistance. And then what else do we have? Well, if they're falling through the air pushes up, but we've got gravity, right? We've got gravity or the weight of this person down. Okay, so if we were to draw the free body diagram, could you do that right now? I think so. I think you could. So air resistance pushes up, right? F of AIR pushes up on the skydiver. And so that's FAIR. And then down, we've got gravity. Zoop. Okay, so I'm going to make this interesting. It doesn't tell us if they've hit terminal velocity. Terminal velocity means constant velocity. It means the fastest a object can move in the sky, and you'll reach terminal velocity skydiving at about 120 miles per hour. All right, let's pretend that we have not hit terminal velocity yet, right? So what I'm going to do is I'm trying to show that this is a larger arrow vector, and I'm not going to use the equality, the congruent lines to show equality. All right, so F of G, right, which is gravity, pulls down on the skydiver. Okay, and therefore we have acceleration. We have positive acceleration down towards the earth. right? Positive acceleration down towards the earth. And if we take a look, right, the motion really would depend, right? If we said up was positive and down was negative, you could say that the motion is negative. Maybe we said up is negative and down is positive. We'd really have to maybe see some type of scenario. If they didn't write that in, you could say that yourself. But the motion, I'm just going to put the direction is towards the ground. Okay, towards the ground. And I think that's okay for now. If you need a moment, please hit pause and make sure that we get all of this information down on our notes. You can always come back and unpause. Let's do this last one right here. Okay, a rightward force is applied to a cell phone in order to move it across the desk with a rightward acceleration. Consider frictional forces. It says neglect air resistance. So notice how here it said don't neglect it, right? Add it in, which is why it was one of our forces. And here it says neglect it, so we can leave air resistance out. But what do we have? Well, we've got the normal force. We have an applied force. We have gravity, which is the weight of the cell phone. And then we have friction, right? Because if you're pushing something across the desk, you're going to have friction opposing this applied force. So take a moment and see if you can draw this out. And I'm just going to put my dot here. See if you can draw out the cell phone moving with a rightward force, this applied force. And if I start too fast, then what I want you to do is just pause the video and draw this in and then come back. In fact, do that right now. Okay, last but not least, let me draw this in so we can see it. It's telling me here also the explanation. So we know that gravity pulls down, right? F of G is down. We know that the normal force is the supportive force from the desk up. And these two are equal because the cell phone's not being pulled through a desk. It's also not like levitating in the air. So we would draw the congruency lines to show at rest in this vertical plane, the up and down plane. Okay, so what we have to do now is look at this applied force. The applied force is to the right. So that's F of APP. Sorry, that's F of APP. And friction is to the left. Now, when I draw this in, the frictional arrow is going to be smaller than the applied force because it's telling me that there's a rightward acceleration. So the unbalanced force to the right has to be larger. And so friction, which is this leftward vector, has to be smaller. So friction opposes the push leftward, the acceleration, or leftward acceleration, and the motion is towards the right. So these are your free body diagram notes. And this is a lot of detail. Mainly what we will be doing is drawing what we have in this third column. When we're asked to draw a free body diagram, we would just need this guy, right? We would just need that guy. That's it. The reason that we give you all of this is so that you can really understand what this picture is showing. Because we have to not only be able to draw this from a scenario, but we have to be able to explain this if we see it. If you have any questions, let us know. And this is what we're going to be doing a lot this week, drawing these free body diagrams. Thanks, guys.